Alright, you guys, here's your video for RSG 1.2. This will be done in class Thursday, December 8th with your substitute. So let's look at the ready. Let me make this bigger here. There we go. So the ready asks you to rewrite each expression as the product of two binomials. A binomial is simply something with two terms. Usually one has a variable and the other does not. So we have repeating binomials here. Okay. That just says that the 2x will get multiplied by this whole thing, and the 7 will also get multiplied by this whole thing. Now you can distribute here, but it's asking us to write it in a certain form. So it's saying that we want it to end up looking like that, where we have one term or one set of terms, one binomial in parentheses, and a different one also in parentheses. So what's going to happen if you look at the example, you're going to take these repeated ones and just make it its own. And then you're going to take what's outside of the parentheses and create a whole new binomial with that. So here we've got repeated 5x plus 3. And then we're going to take this 2x plus 7 and put that in its own set of parentheses. And that's it. That's all you have to do. You don't actually have to solve that, which you can't really do because there's no equal sign. You could simplify it. You could distribute it out, but it's not asking us to do that. So we're not going to do that. Okay, so here in 2, we have repeated x plus 1s. So we'll just write that out here. And then we'll take what's inside, or sorry, outside the parentheses, and combine them in their own set of parentheses. Here we have repeating x minus 10. Then we're going to take this stuff and do that. Okay. Repeated. And then write what's outside in its own. Okay, I'm pretty sure you can do the rest of these on your own based on what you've seen here. I really want to get to the set. And I'm going to use a pencil because I don't trust myself with pen on this stuff. Okay, so the set is asking you to determine a few things. Is it arithmetic or geometric? So in other words, is it linear or exponential? Or is it quadratic? That is a possibility here. Okay, and it all starts by figuring out the rule. So let's figure this out here. 64 to 128, that's a difference of 64. 128 to 256, that's a difference of 128. So you can see that it's not going to increase by the same thing every time. But before we jump to saying it's an exponential, or before we jump to saying it's a quadratic, we want to check and see if it's possibly exponential. So can we multiply by 2? And if that doesn't work, we can maybe try multiplying by 3. If you're checking to see if something has a multiplier, you can always just pick 2 numbers and divide them. And that will give you a multiplier if there is one. And it looks like it is 2. And we can check that as we go down. 128 times 2, that is 256. 256 times 2, that is 512. And then 512 times 2 is 1024. So the type of function is exponential. The nature of the change is a ratio or a multiplier. And now we have to write our explicits here. So for an exponential, you have your zero term, your rule and your multiplier, and your x. If you notice here, we don't have a zero term. We could get one if you wanted to, or we could use this sixth term and just make sure that we say we used the sixth term by putting that up here in our exponent. This x minus 6 indicates that we used the sixth term and not the zero term. If you wanted to go and get the zero term, you would divide by 2 all the way back. So the fourth term is 16. The third term is 8. The second term is 4. The first term is 2, and the zero term is 1. So if we wanted to write it with the zero term, it would look like this. The zero term is 1. Our rule is still 2. And the x is just x because we don't have to indicate that we used the first term or the second or third or fourth, because we didn't. We used the zero term. So we can just leave the x. Recursive is always the same. This x minus 1 is always there. That just means it's your previous term. We're not necessarily subtracting 1 from anything. So x minus 1 and then multiply by your rule. Okay. So now we're going to check this one. Let's figure out the rule first. That is an increase of 13. Okay, see if you can figure out the other increases, and then we'll talk about how to build that equation. So if you worked that out, you can see that it goes up by a different amount every time. It's not adding or subtracting the same thing every time. It's not multiplying by the same thing every time. It is increasing, but not by the same thing. Let's check our second difference. If that is consistent, then we have a quadratic here. So plus 2, plus 2, plus 2. So this is a quadratic. And you can just say it's a different amount every time. Okay. And the explicit equation can be pretty tricky, so can the recursive, especially since we don't have a zero term right here. Okay, but we talked about this yesterday in class, at least I know second hour did, that in a quadratic, you're always going to have something being squared. Whether it's x squared or y squared or b squared or whatever, there's always going to be an exponent in there somewhere. Okay, so we can build our explicit by looking at the relationship between our x and our f of x. Okay, what do we have to do to x to get the f of x value? Okay, and the first thing that's easiest to do is just try squaring x. because we always know that a quadratic will have a square in it somewhere. So we always start by squaring it to see if that'll get us to our answer or close to it. And in this case, it gets us our answer exactly. But let's see if it works all the way down. 7 squared is 7 times 7. And that is 49, so that one checks out. 8 squared is 8 times 8. That's 64, that checks out. 9 squared is 9 times 9, that checks out. And 10 squared is 100. Okay, so for every x that we have, we need to square it to get our y, or our f of x. So when we write our equation, we are simply saying what has to be done to x to get f of x. And in this case, we have to square it. And that's it. That's all we have to do to our x to get our y. And so that's all our equation needs for the explicit. The recursive is a little harder. It still has the x minus 1 in it, still talking about the previous term. But what you're adding now is actually the expression for the first difference. Okay, that's what you're going to tack on to the end of a recursive. Instead of simply a rule, which is a whole number, instead of just saying x minus 1 plus 3 if you're adding 3 every time, we need to find an expression for the first difference right there. Okay, so I want to write that. I changed my mind on how I want to do that. Okay, let's look at our first difference, 13, 15, 17, 19. What's the rule? Well, you can probably see by now that the rule for the first difference, this group right here, the rule for that is a plus 2. So the rule of the rule. Okay? And it started at our first number. Okay, we could go back to where our 0 term is. And this pattern will apply. Okay? The pattern starts at the first term. So when we go to write our recursive, we'll still have our x minus 1 to mean the previous term. But we're going to have an entire linear or arithmetic expression to tack on to the end. Okay, so our pattern here in our first difference is a plus 2, and it starts at the beginning. This pattern starts at the beginning. And so we're going to say, all right, our rule is 2, and that begins at our very first term. That's the minus 1. So there's your recursive. So essentially what we're doing is we're putting in the rule, x, and we're saying the rule starts at the first term, which is usually the case. Okay. Most of the time, the only thing that changes from one recursive to the next is the rule. And I know this is kind of an overwhelming problem. We're going to look at another one in a minute, but yeah. This one, I'm pretty sure you guys can do. Okay, I want you to find the rule, figure out if it's arithmetic, geometric, or quadratic, and write the explicit and recursive equation for that. Notice that we start at the 6th term. It'd be pretty easy to go backward and find the 0 term, but you could also use point slope form, which is the following. Okay, it's really handy if you start at something like the 6th term and you don't want to go all the way backward to the 0 term. So your rule will go here. You'll put an x, and then you'll list one of the x values, followed by its corresponding y value. Okay, so if I wanted to use 8 and 15, I'd see that the rule is 2, x, my x value is 8, its y value is 15. But then I would have to distribute and combine like terms. Negative 16 and positive 15 is a minus 1. Okay, so there's your explicit. Your recursive equation, again, is just x minus 1 followed by the rule. So I'm pretty sure you guys can do C on your own. Okay, and we'll go to D and E and F. Okay, we do have a 0 term here, which is nice, but we still need to figure out what the pattern is. If it's arithmetic, if it's geometric, if it's quadratic. Okay, so negative 17 to negative 12. If you think about it in terms of temperature, it's negative 17 degrees outside, and later on it's negative 12. Did the temperature go up or down? It went up by 5. Okay, and that pattern seems to continue. And I'm going to let you guys write the equations for this. Just because I don't do it in the video doesn't mean it's not required. This is required. Every problem in the Ready, Set, Go is required. Okay, let's look at E. This is pretty tough. Those first 2 terms are a little tricky to see. But as you go down a little further, okay, from 1 to 5, you can either look at it as a plus 4 or a times 5, and then figure out from 5 to 25 which one works. Is it a plus 4 or is it a times 5? And we can kind of see that it's a times 5, which makes it geometric, and I will let you figure that one out too. Geometric explicit, again, is your 0 term times the rule raised to your exponent. All right, let's look at F. If you need to pause the video to finish D and E, go ahead and do that. All right, let's look at this. Notice that our X terms are all the same in these 3 problems. They've given you an arithmetic, they've given you a geometric. Let's see what they give us here. That's a plus 3, a plus 1, sorry, minus 3, minus 1. That's actually a plus 1, and that's a plus 3. Okay. All right. This is definitely quadratic. We don't have anything constant, whether it's adding, subtracting, or multiplying. And so that just leaves quadratic as an option. But we need to figure out the second difference as well. So to go from negative 3 to negative 1, that is an increase of 2. So we definitely know we have a quadratic. It has different rates of change. Okay, now we need to write an explicit and a recursive. So again, I like to just kind of write another table. Because if I know a quadratic has to have a squaring in there somewhere, then I can start there. Okay, I'm actually going to make this a little bigger. All right, so let's square this. And, well, let's get these in here first. Okay, so once I square my x, that gives me positive 4. To get from 4 to 9, I still have to add 5. So what I've done so far here is I took my x, I squared it, and I added 5 to get from my x to my f of x. Okay, so I'm going to continue doing that. First thing I'm going to do is square it. But I still need to get from 1 to 6. And again, I have to add 5. So for this set of numbers, I squared my x and added 5 again. Here I'm going to square 0, which is just 0. But I need to get from 0 to 5. So I need to add 5. So again, I squared my x and added 5. And that got me from my x to my f of x. 1 squared is 1. To get from 1 to 6, I need to add 5. 2 squared is 4. To get from 4 to 9, I add 5. So I'm still doing this x squared plus 5 all the way down. And that is my explicit. Notice that your recursive doesn't generally have an x squared in it. And that is because the format for that is based off of the linear first difference. And a linear never has an exponent. Linear is the same as an arithmetic. We don't have an exponent in those. So you're not going to see that in the recursive. The recursive is really talking about, okay, what do I have to do to my first term to get my second term? What do I have to do to my second term to get my third term? Okay, that sort of a thing. So we need to look at our first difference here. Okay, our first difference is right here. Our rule is a 2. So there's our rule. Okay, and this rule starts applying at the first term. And by the first term, I mean the first term of our second difference. Not this first term. I mean the very first term of the first difference. Okay, because it applies to the very first term of the second or the first difference, that's where the 2 plus 1 or 2x minus 1 comes in. Okay, so if we look at this again, okay, we've got a minus 3, a minus 1, a plus 1, and a plus 3. The first term of our first difference is minus 3. Okay, and the plus 2 second rule starts applying right away. Okay, it starts applying from the first term of that first difference, which is where this 1 comes from. And there's your recursive. Notice your recursive is actually the same as your first one. Right here in letter B. The rule was 2, and it applied to the first term of the first difference. Okay. Graph the functions from the tables in problem 9. So you're going to go back to this. You're going to graph all of these now. Okay. And the directions do say to make sure you label your axes so that all the numbers show up. So if you look at 9A, you go clear up to 1,000. So we might need to look at that really carefully here. Make sure that you are labeling your graph correctly. These are your X values. These are your Y values. Okay. And so I can't look at both of these at once, but you can. So we go from 64 to 1,000. So I would maybe start with 100. So that I know that 1,000 shows up. It's still not perfect. We're still going to be a little bit off because of the 1,024. But now we can look at our table and say, okay, my sixth term is 64. In a table, these numbers are an ordered pair. Okay, so 6 and 64. Well, 64 is less than 100, but a little more than half, so I'm going to put it about right there. 128 is just a little bit over 100 in this case. 256 is about right in the middle between 200 and 300. 512 is just barely over 500, and then 10 is 1,024. But look at this. Look at what we have here. We have a very defined curve happening. Okay, and that makes sense because it's exponential, but it's never going to hit the x-axis because dividing over and over and over again will never get you to 0. It's kind of a weird thing to think about, but it is true. Okay, let's go to B. Check out your numbers. Make sure that you label your graph appropriately so that all the numbers fit. I can still do 1 through 10 down here. That's not bad, but I need to look at my Y values. So we ended 100, so I could probably go up by 10s here. Okay, I'm good there, barely. We already determined that this is a quadratic, so we should expect some sort of curve in our graph. So let's find out. We started our sixth term, which is 36. Our seventh term is 49, so right before 50. Our eighth term is 64, kind of right in the middle there. Our ninth term is 81, and our 10th term is 100. Okay. This is almost linear. Because the difference in our first difference is so slight, this is almost linear, but not quite. So the bigger the second difference, the more defined that curve will be, okay, in a quadratic. Exponentials are going to be curved no matter what, but in an exponential or in a quadratic, the bigger your second difference, the more drastic your curve will be. Okay, so let's go graph, I think it was F. Yeah, F is our other quadratic, so let's graph that one. This has a second difference of 2 also, so I would expect us to not have much of a curve again. But look here, you've got a couple negative x values, which means you're going to need your left-hand side of your x-axis. Okay, you don't have any negatives in your f of x values, so you won't need anything below the x-axis, so you could actually do, whoops, this. So here's your x-axis, here's your y-axis. And in the directions, it's stated to make sure that you label your graph appropriately. And this is part of what they were talking about. Make sure you put your axis in the right place so that you have all the right numbers that you need. So F, my negative second term, so I need to go to -2 on my x. My negative second term is 9, and I'm just going to label these like this because we actually have room. Our numbers don't get very big. So when my x is -2, my y is 9. When my x is -1, my y is 6. When my x is 0, my y is 5. When my x is 1, my y value is 6. When my x is 2, my y value is 9. Well, that's interesting. What the heck is that? We haven't seen that yet. Okay. Look at our table, though. We have a y value of 9 in 2 places. Our x values for that just happen to be opposites of each other. We have 6 in 2 places. Our x values just happen to be opposites of each other. Okay, this graph is called something. It's called a parabola. And that is like the graph for a quadratic. Quadratic will generally result in a parabola. So this is what you're going to get used to seeing over the next little while. Is quadratics end up looking like that usually. I'm pretty sure you can graph the other ones on your own without my help. I do want to show you what the Go is asking you to do. Find the greatest common factor. So the largest number that can go into both numbers. Or in other words, the largest number that both numbers can be divided by. Okay. So I like to list my factors. And you can see that there's only one that they share, so the GCF for this one is 5. 12 is divisible by 1, by 2, by 3, by 4, by 6, and by 12. 32 is divisible by 1, by 2, by 4, by 6, by 8, and by 16, and by 32. So you find the biggest number that they have in common. There's a few in common here. They share a 1. They both have a 2. They both have a 4. But we're looking for the biggest one that they share. And in this case, it's a 6. Okay. Let's go down to 17. 22 is a prime number, actually. No, it's not. Just kidding. So 2 times 11 and then 1 times 22. 33 is divisible by 1 and 3 and 11 and 33. And then 99 is divisible by 3 and 9 and 11 and 33 and 99. So we're going to look for the biggest one they all share, and it is 11. That's what the Go is asking you to do. And then once you're done with 19, that's the end of the RSG. And that is all.